you have this mathematical solution, which has a black hole and a white hole, and a wormhole connecting them. Is that information somehow imprinted in the Hawking radiation? When the black hole's gone, hundreds, thousands of physicists have spent 50 years trying to understand what actually happens. And the current consensus now is that the information comes out again.
Could black holes hold the secret to a more profound understanding of reality, space, and time through a quantum theory of gravity? Black holes, one of the universe's most fascinating and enigmatic phenomena, are found in the area we're discussing. Despite their immense power, these colossal beings are almost undetectable to us. Nevertheless, we have gone from knowing virtually little about them to researching them in greater detail than ever before because of decades of research. And things took an even more startling turn right when we believed we had learned everything there was to know. Recently, Brian Cox disclosed that scientists have finally seen what's inside a black hole. We believe we have complete control over the physics at a location known as the event horizon, which makes black holes fascinating. We know what's going on, but our two fundamental theories of nature, general relativity and quantum theory, are fundamentally at odds. For theoretical physicists, the goal of combining these two major pillars of 20th and 21st century physics into what is sometimes called a quantum theory of gravity is somewhat of a holy grail. Thus, black holes are pushing us to think more deeply about time and space. Black holes, in my opinion, are the keys to comprehending the cosmos because they provide fresh perspectives on scientific topics that may have previously gone unnoticed. Let's go over the fundamentals before delving into what Brian Cox found. Even while most of us comprehend black holes in general, there are still some things we don't know. The black hole is surrounded by an event horizon. In a way, it establishes the line separating the black hole's interior from the outside world. You cannot escape the gravitational attraction of a black hole if you cross the boundary and enter the inside of this sphere, even if you are able to travel as quickly as light. However, the notion that the event horizon is a location in space where time pauses when viewed from the outside was another explanation of the event horizon that perplexed people throughout the history of black hole study. And from an exterior standpoint, that is a clear prediction of Einstein's theory of relativity. However, a fundamental issue remains unresolved: what is at the core of a black hole? Black holes were predicted by Albert Einstein's general relativity theory, which was first presented in 1916. Black holes had just been a theoretical idea at the time. Scientists did not discover proof that they truly existed until the 1960s. They noticed an unusually bright blue star that was generating X-rays when they were examining the Cygnus constellation. Not only was this star motionless, but it was circling a huge, unseen object. They discovered that the X-rays were being drawn inside the enigmatic item rather than simply moving on their own after more research. The term black hole was therefore created, because it offered hard proof that black holes weren't merely a figment of Einstein's imagination. This finding was revolutionary. But it also made the existence of this enigmatic phenomenon in space real, which made more research imperative. This newly discovered black hole, Cygnus X1, which is situated in the Cygnus constellation some 6,000 light-years away, immediately caught the attention of scientists worldwide. Being around 14 times brighter than the Sun and extremely dense, it produces a gravitational force so strong that not even light can escape, making it an unusual discovery. It is for this reason that it is called a black hole. There is something both fascinating and frightening about the idea of a black hole. It's an area of space where gravity is so strong that light cannot escape. Anything that approaches too closely will be drawn in and never come out again. But it is even more important that we learn as much as we can about these cosmic secrets because of that very peril. Were we just beginning, or was this the end? As it happens, the latter is the case. After Cygnus X1 was discovered, researchers started looking for more black holes. They currently think that the Milky Way alone may contain more than 100 million black holes. But we don't know the precise number because it's so hard to find them. Black holes are very important to investigate because we do know that there are probably millions of them in our own galaxy. The gravity of black holes is always the primary worry. Anything that crosses their threshold is crushed to the point of becoming a singularity due to the strength of their gravitational pull. To put it another way, black holes draw everything in like cosmic vacuum cleaners. The fact that a person would be stretched out until they became a thin line if they fell into a black hole is among the most unnerving parts of studying them. The person would pass away before achieving the final shape because this procedure is gradual. Let's just say that even if they are everywhere, it is absolutely not a good idea to fall into one. Does that, however, imply that we are in danger? Despite being 500 light-years away, the nearest black hole to Earth is nonetheless close enough to cause concern. The M87 black hole was the subject of the first clear image of a black hole published by scientists in 2021. Over the course of several nights, this black hole was photographed, with each image yielding further details. In order to fill in the gaps and discover that black holes contain 3 separate layers, the researchers had to stitch the photos together. Contrary to popular belief, they are not simply a vast, empty emptiness. That's not all there is to it. You have to go through 2 layers before you can even get to the emptiness at the center of a black hole. The event horizon, or simply the point of no return, is the first. There is no turning back once you reach the event horizon. You will be drawn into the black hole, and things only get worse from there. The area where light circles the black hole is known as the photon sphere, and it is the next layer. Light entering this region will be imprisoned and unable to break free from the gravitational pull of the black hole. The singularity, the third layer, is finally reached. Everything that falls into the black hole is compressed to an unthinkable extent here, eventually leading to a singularity. The singularity is the point in spacetime where we can no longer foresee what will happen next since the laws of physics as we know them no longer apply. The density becomes limitless at the singularity, and the laws of physics vanish completely. All of this is made much more astounding by the fact that each black hole is completely different. Despite having the same fundamental 3-layer structure, their methods of operation may differ greatly. We could simply mount telescopes and conduct in-depth research if this were any other event. But that's just not feasible with black holes. Only by examining the radiation they release and the gas and dust around them can scientists gain an indirect understanding of them. Anything that crosses the event horizon is pulled toward the singularity, where it is crushed into an incredibly tiny point, making it impossible to send a probe like the Voyager into a black hole. Billions of dollars would be wasted simply to see a probe destroyed the instant it approaches too closely. Despite the fact that black holes are 3-dimensional things, scientists are forced to investigate them in 2 dimensions due to this significant barrier. Every black hole is different, and when we attempt to look within, the laws of physics fail, which makes things much more complicated. This implies that the study of black holes is not exactly amenable to conventional scientific methodologies. Despite this, researchers have continued to put in a lot of effort. Black holes are the subject of innumerable ideas and explanations, and the more that is discovered, the more intriguing the subject becomes. The idea that black holes develop from collapsing stars is among the most intriguing hypotheses about their formation. A star can no longer produce enough energy to counteract gravity's inward pull when its fuel runs out. The star consequently starts to collapse, getting denser and smaller as it goes. This collapse can go on until a singularity is formed if the star is big enough. NASA scientists studied the core of the galaxy M87 to learn more about black holes. A strong maelstrom of superheated hydrogen gas was seen swirling at an astounding 1.2 million miles per hour by astronomers. It should have exploded in all directions due to the spinning gas disk's tremendous energy, yet it didn't. Scientists came to the conclusion that this couldn't occur because of a huge object at the galaxy's center. With a mass of 2 to 3 billion suns, this massive mass could only be a black hole. That being said, there are several theories concerning the spin of black holes. In 1963, Roy Kerr, a mathematician from New Zealand, provided the best explanation for a spinning black hole using Einstein's equations of gravity. Kerr showed that a spinning black hole will generate a narrow disk or ring of fire rather than collapsing into a point as previously believed. Centrifugal forces would keep the disk from collapsing since it would spin so quickly. The area around a black hole where the laws of physics start to fail is called the ergosphere, and it is this rapidly spinning disk of stuff. However, Kerr's solution's prediction of an Einstein-Rosen bridge, also known as a wormhole, was its most intriguing feature. This hypothetical spacetime link connects two distinct parts of the cosmos, or possibly two parallel universes. According to the theory, if someone were to fall into a black hole, they would be drawn into a tunnel through a ring of fire and emerge out a white hole in a parallel universe instead of being crushed to nothing. We must examine the idea of spacetime in order to understand how this operates. According to Einstein's theory, time and space are intertwined and form spacetime is a four-dimensional fabric. When mass-containing things disrupt this fabric, they produce a gravitational field that pulls other objects toward them. Consider a piece of paper as the spacetime model. Basically, you may depict how objects move through spacetime by placing 2 points on the paper and drawing a line between them. Imagine being able to make a shortcut between those 2 points by folding that paper in half. The concept of a wormhole, which is a shortcut through spacetime that immediately joins two distant sites, is basically this. Despite the fact that no one has ever seen one up close, wormholes are a real prediction of general relativity and are not merely a sci-fi idea. Wormholes would collapse relatively immediately due to their intrinsic instability. But the presence of an Einstein-Rosen bridge would suggest that black holes could be portals to other parts of spacetime in addition to being cosmic vacuum cleaners. So what if we could travel through time and space using a wormhole? Sadly, the answer is probably no, at least not quite yet. It's unlikely that we could use a wormhole for faster-than-light travel, even if we could stabilize one. The speed of light is the absolute maximum speed at which anything can travel through spacetime, according to Einstein's theory of special relativity. Despite this, physicists have been fascinated for decades by the notion that black holes and wormholes could serve as portals to other regions of the universe or even to alternate eras. If we could somehow make it a reality, the idea that there might be shortcuts to the very fabric of spacetime, allowing travel over great distances or even back in time, could be revolutionary. Named for the mathematician Roy Kerr, who initially defined it using Einstein's equation of gravity, a Kerr wormhole is among the most intriguing possibilities in this subject. In essence, this kind of wormhole is a hypothetical tunnel across spacetime that might connect two far-off locations, such distinct worlds or discrete points in time within the same universe. Like Alice in Wonderland's Looking Glass, the Kerr wormhole is frequently pictured as a ring-shaped doorway. In the narrative, Alice was taken to a world where animals spoke in riddles and reasoning wasn't always consistent after passing through the looking glass. Theoretically, traveling through the Kerr ring could take a person to a different time or universe with drastically different physics laws. But once you're there, those changed laws may feel perfectly natural. Wormholes as a means of traveling across time or between stars is an exciting concept, but it also causes controversy and disagreement among physicists. Some have noted that because of the strong radiation and subatomic pressures surrounding their entrances, wormholes, particularly Kerr wormholes, may be unstable or impossible to navigate. Einstein's equations of gravity, which are used to explain both black holes and wormholes, are criticized for only describing gravity and not the quantum forces governing radiation and subatomic particles. A new theory that can reconcile the quantum theory of radiation and the laws of gravity is needed to fully comprehend these events. The scientific world refers to this as a theory of everything, a single theory that combines quantum theory and Einstein's theory of gravity. For many years, renowned theoretical physicist Brian Cox has been developing such a theory. Superstring hypothesis is the only hypothesis that has demonstrated genuine potential, despite the fact that there are several theories of what this theory might be. The concepts of radiation and gravity are combined in superstring theory. It suggests that the universe is like a symphony of subatomic particles, which are really just tiny vibrating strings. Different particles correlate to different vibrations of the superstring, much as different violin string vibrations produce different musical notes. The idea that a string can create black holes, wormholes, and other unusual solutions to Einstein's equations by distorting the surrounding fabric of space as it travels through time is one of the fascinating features of superstring theory. This indicates that superstring theory helps explain many of the odd events we see in our universe, in addition to bringing Einstein's theory of gravity and quantum theory together. But there's something about this notion that, despite its apparent simplicity, becomes more complex upon closer inspection. According to superstring theory, spacetime has 10 dimensions in which there are microscopic vibrating strings. Compared to the 3 dimensions of space and 1 dimension of time we encounter on a daily basis, that is a significant leap. Although physicists have developed models to help us understand, it is difficult to imagine what these additional dimensions would look like. Envision a 2-dimensional pond where fish are only aware of its breadth and length. They cannot even begin to conceive what it would be like to live in a 3-dimensional environment. To them, height does not exist. Although the fish cannot truly feel the impacts of height, they can observe them if rain makes ripples in the pond. Similar to this, scientists believe that although we cannot directly perceive the additional dimensions of spacetime, we can observe how they impact our reality. For example, superstring theory shows that vibrations of strings can produce energy waves that pass through these additional dimensions. These waves might manifest as particles with various characteristics, such as mass and charge, similar to the particles that comprise everything we perceive. Superstring theory might explain gravity and all other particles and forces in the universe in this way. The problematic issue is that we are unable to directly explore these additional dimensions since they are so small. Only the 4 dimensions that we are aware of, length, width, depth, and time, allow us to take the most precise measurements. How can we be certain that these additional dimensions exist, then? One theory is that we can't see them because they are so tightly curled up. Imagine an ant moving across the surface of a sheet of paper that has been wrapped into a cylinder. You might not even notice the curvature. According to superstring theory, there may be more dimensions of spacetime that are coiled into minuscule spirals or loops that are invisible to the naked eye. These dimensions influence the behavior of the strings in the theory even if we cannot see them. One theory is that these additional dimensions were more obvious at the Big Bang, when the cosmos first formed. Indeed, according to some interpretations of superstring theory, the cosmos began with 10 observable dimensions. However, the extra dimensions started to collapse and curl up as the cosmos cooled and expanded, leaving us with only the 4 dimensions that are visible to us now. We may eventually find evidence of these hidden dimensions all around us if this theory is correct. Superstring theory is quite complicated mathematically. It has given rise to previously unexplored branches of mathematics. However, one significant obstacle has been resolving the mystery of a quantum black hole, which no scientist has yet to solve. According to renowned Princeton physicist Edward Witten, superstring theory is 21st century physics that fell accidentally into the 20th century. Recently, a breakthrough was reached by certain physicists. They discovered that, although only in 2 dimensions and not all 10, string theory could be able to resolve the quantum black hole problem. Many experts believe that since the equations are well-defined but challenging to solve, the answer will eventually be discovered. But until then, it's probably too early to start planning time travel excursions or travels to distant universes. One thing is certain, particularly with regard to black holes, there are far too many unanswered questions and even more answers that have been suggested. Brian Cox has provided guidance on how we could ascertain which of these outlandish theories is accurate. He noted that string theory is not the only field that faces the problem of endless solutions. In actuality, there are an endless number of solutions to many well-known theories. Newton's laws, for example, may forecast the motion of many objects, ranging from spacecraft to pebbles, but you must describe what you're attempting to analyze in order to do so. We refer to these requirements as beginning conditions. In a similar vein, you must specify what string theory is explaining. String theory's beginning circumstances, however, are closely related to the Big Bang, in contrast to other hypotheses. This implies that we need to specify the unidentified conditions that existed at the time of the Big Bang. There are several approaches to this problem. Finding the Big Bang's initial circumstances experimentally and then using string theory to describe how the universe has changed since then is one possibility. Surprisingly, string theory already has answers that, based on plausible approximations of its nature, describe how the world evolved from the Big Bang. This is a significant advancement. The hypothesis that string theory establishes its own beginning circumstances is a more ambitious one. Although this method is less common and more complicated, it does significantly reduce the number of options. But Brian Cox presents a whole different viewpoint. The Big Bang might not have been as large as we usually think. He said it didn't create a loud noise as the name might imply, nor was it a huge explosion as people believe. The Big Bang theory merely asserts that the event occurred without elucidating its cause or mechanism. A theory explaining what happened before the Big Bang is what we really need. String theory can help with that. According to string theory, our world may have formed from the collision of two distinct universes or may have sprung from another one, much like a child born from its mother. Wormholes, which are essentially tubes connecting two bubbles, are the name given to this connection between universes. The possibility that we have already discovered proof of an umbilical cord connecting our universe to another is intriguing. We might not even be aware that we are living inside a black hole. Consider this: we can only see 4 dimensions because we are limited to them. The black holes we investigate may be wormholes leading to other dimensions, and we may be within a black hole. However, what are your thoughts? Is there any chance that this theory is correct? Please leave a comment below with your opinions, and remember to give this video a thumbs up if you liked it. We'll see you at the following one.